Hi, everybody. Thank you for tuning into my talk, and thank you to the organizers for inviting me. Also, thank you to Alvaro and Keith for helping me with the slides for this talk. This is joint work with my advisor, Alvaro Lozano Lopero. This work is about understanding the algebraic properties of elliptic curves defined over the rationals by studying the Galois representations attached to them. The goal is to classify rational torsion subgroups, but in the bigger picture, it tries to understand what the possible images of the Galois representation can be mod different prime powers. There's also an aspect of finding or disproving the existence of rational points on modular curves. Let's start with the dictionary of terms we will use. A rational elliptic curve E is a smooth projective curve cut out by a homogeneous equation of degree 3 you see below with rational coefficients. There is a point at infinity I will call O. If we dehomogenize, we get an affine equation which eliminates the z variable, so long as we remember this point at infinity. An elliptic curve has a structure of an abelian group with identity O under the following operation. So to add two unequal points P and Q in E, draw a secant line connecting P to Q. This secant line, drawn here in green, intersects the curve at a third point. Drawing a vertical line through this third point, the vertical line intersects the curve at a second point, which is P plus Q. So to add points that are equal to each other, like let's say if we want to find 2Q, instead of drawing a secant line, let's draw a line tangent to E at Q, drawn here in red, and repeat the process above by finding the third point, etc., etc. This operation makes E into an abelian group. Let E be an elliptic curve. A point P is defined over Q if P is the identity or of the form A comma B for some pair of rational numbers A and B. The set of all elements of E defined over Q is denoted E of Q. We can also call the points of E defined over Q the rational points of E. The Mordell-Weil theorem, here stated in a little simplified form, was proven by Louis Mordell in 1922 and extended by André Weil in 1928. It states that the set of rational points of E is a finally generated abelian subgroup of E. But for this talk, we really only care about the rational torsion subgroup of E, the set of elements of E of Q of finite order denoted E of Q torus. In 1978, Barry Mazur classified the rational torsion subgroup of all elliptic curves defined over Q. They are one of the 15 groups, the cyclic groups of orders 1 through 12, but not 11, and the bicyclic groups Z-mod 2 cross Z-mod 2, Z-mod 2 cross Z-mod 4, Z-mod 2 cross Z-mod 6, and Z-mod 2 cross Z-mod 8. The groups that are not cyclic are what we call having full tube torsion. So let E be an elliptic curve and n a positive integer. The set of all elements of E with order divisible by n, which I denote E bracket n, is isomorphic to a group to Z mod nz squared. We call this the n torsion subgroup of E. Let's denote the absolute Galois group of the rationals as GQ. GQ acts on E by fixing O and acting on the other points A, B in the natural way. This action commutes with the group operation on E, and so GQ also acts on E bracket n. Picking a set of generators of E bracket n, we get the mod n representation attached to E. Okay, great. Now let's talk about the maps between elliptic curves. Let E and E prime be elliptic curves. An isogeny mapping E to E prime is a morphism phi such that phi maps the identity of E to the identity of E prime. Phi is in fact a group homomorphism. The degree of an isogeny is equal to the cardinality of its kernel. From now on, if an isogeny has finite degree equal to D, I will call it a D isogeny, like for example, a 5 isogeny or a 10 isogeny, etc. E is said to be isogynous to E prime if there exists a non-constant isogeny mapping E to E prime. This relation is in fact an equivalence relation with the symmetric axiom satisfied by the dual isogeny. The set of all rational elliptic curves isogynous to E is called the isogeny class of E. Now, how do we actually get isogenies from E? Where do we start? So the following theorem can be found near the end of the third chapter of Silverman's Arithmetic of Elliptic Curves. Let E be an elliptic curve and H a finite subgroup of E. There is a unique elliptic curve up to isomorphism E mod H and an isogeny phi sub H such that phi sub H maps E to E mod H with kernel H. E mod H is said to be generated by H. If, moreover, the Galois group stabilizes H, then the isogeny phi and the curve E mod H are rational. In this case, we will say that H and phi sub H are Q-rational. This theorem gives us a great way to find isogenies of E and curves isogenous to E just by looking at E. This theorem is extremely important. So that's great, but isogeny classes are just abstract sets so far. How do we put a little more organization to them? So let E be a rational elliptic curve. The isogeny graph of E is simply a visualization of the isogeny class of E, with edges being isogenies generated by the finite cyclic Q-rational subgroups of E, and vertices being elliptic curves generated by these same finite cyclic Q-rational subgroups of E. For example, consider this rational elliptic curve here. It has an isogeny class of size 4. With the isogeny graph, there is a clear way of how the isogenous curves fit together in a sense. So these are a couple of the questions Alvaro and I asked ourselves to kind of start the problem. What is the point if we let E prime be isogenous rational elliptic curves? If I know the torsion subgroup of E, can I reasonably guess the torsion subgroup of E prime? What if I do not even mention another curve E prime? Can I reasonably guess the possibilities of torsion for each curve isogenous to E without a mention of E prime? Can I find the possibilities of torsion for each vertex of the isogeny graph of E? So each question is slightly more complicated than the one before it. So let's make a new definition that Alvaro and I came up with. Let E again be a rational elliptic curve. The rational isogeny-torsion graph of E is the rational isogeny graph of E with the classification of the torsion subgroups of each vertex. So for example, take the rational elliptic curve we saw 2 slides ago. On the left is the rational isogeny graph of E. On the right is the fully characterized rational isogeny-torsion graph of E. So can we understand these rational isogeny-torsion graphs on the right? So let E be a rational elliptic curve. This slide shows that classifying the torsion subgroups of the curves in the isogeny class of E is not enough to determine the rational isogeny-torsion graph of E. For example, the first graph can be distinguished from the second and third because the first graph does not have a cyclic group of order 8, while the other two do. But the second and third graph have the same exact groups, but with a different arrangement of torsion subgroups on the graph. So knowing the torsion subgroups of the isogeny class is not enough to classify the rational isogeny-torsion graph. But do we really even know where to start in classifying these rational isogeny-torsion graphs? So Sarah asked the question whether the isogeny class of a rational elliptic curve has at most 8 curves. In 1980, Monsieur Kenku proved not only this theorem, but significantly more. Kenku's theorem is cited as the answer to Sarah's question. It is, in fact, this isogeny class of a rational elliptic curve is a set of size at most 8 elements, but that is not the full strength of Kenku's theorem. In fact, what Kenku really proves is so much more. He classified the size and shape of all possible rational isogeny graphs. There are 4 types of rational isogeny graphs, which Alvaro and I called as linear graphs, rectangular graphs, graphs of T-type, and graphs of S-type. And so we will go over examples for them soon. But the main question we asked ourselves is, can we classify all rational isogeny-torsion graphs? In other words, can we classify the size and shape of all rational isogeny graphs and the torsion groups of their vertices? The answer to that question is yes, and here is our main result. So there are in fact 37 rational isogeny-torsion graphs, 12 of which are linear, 8 of which are rectangular, 13 of which are T-type, and 4 S-type. And we will describe them all in the following tables. These are the examples of all the linear graphs. So L1 means one vertex, L2 means two vertices, the subscripts mean the vertices in the graph, etc. So these are pictures of the graphs themselves. These are examples of all the rectangular graphs. So R4 means 4 vertices, R6 means 6 vertices, etc. These are the pictures of all the R4 graphs. These are pictures of all the R6 graphs. These are examples of all the T-type graphs. These are all the T4 type graphs, so 4 vertices. These are all the T6 type graphs with Z2 cross Z2 torsion. These are all the T6 type graphs with Z2 cross Z4 torsion. These are all the T8 type graphs with Z2 cross Z2 torsion. These are all the T8 type graphs with Z2 cross Z4 torsion. And this is the only graph with Z2 cross Z8 torsion. These are the examples of all the S-type graphs. These are the two examples of the S-type graphs with a point of order 3 defined over the rationals. Notice we have a Z2 cross Z6. And these are the two S-type graphs with no point of order 3 defined over Q. So notice there are no Z2 cross Z6s. So let's talk about some of the proofs that went into solving this question. We never had trouble finding rational isogeny torsion graphs, as LMFDB provided examples for all of them with a simple search, so long as we applied Cancu's theorem correctly and knew what graphs to look for. We only really needed to prove which graphs did not exist. So here are examples of 27 isogenies. So the following two graphs are examples of 27 isogenies that do in fact exist. The third graph on the page does not exist. So the reason for this why is that if we have a linear graph for 4 vertices, then one of the curves has a 27 isogeny. A curve with a 27 isogeny corresponds to this single J invariant here. This J invariant is neither 0 nor 1728. And if we let P be a non-trivial point in the 9 torsion, then attaching the x-coordinate of P to the rationals gets you a number field of degree 3, 6, or 27, not 1. So we cannot have rational 9 torsion. Another way of seeing this is that this is a CM J invariant. So all curves with with the 27 isogeny are CM, and by the classification of torsion, rational torsion on CM curves, no CM curve with a 27 isogeny can have a 9 torsion. So actually, this is the only type of graph that exists exclusively for CM curves. No non-CM curve can fit in a graph with a 27 isogeny. So in the interest of time, let's skip the following examples. These are for classifying 21 isogenies. It's very similar to the proof of classifying 27 isogenies. Let's move on to classifying T4 graphs. So let E be a rational elliptic curve with 4 curves in its isogeny class and having full 2 torsion. Then the torsion subgroup is precisely the 2 torsion subgroup of E. So what are the possible isogeny torsion graphs of E? So here I drew the rational isogeny graph of E, but what can the torsion subgroups of the vertices be? We know the middle curve's torsion subgroup is Z2 cross Z2. What about the 3 corners? So the finite cyclic Q rational subgroups of E are precisely the ones generated by the points of E defined over the rationals P, Q, P plus Q, and the identity. E mod P, E mod Q, and E mod P plus Q all have cyclic rational torsion. E has a point of order 2 defined over the rationals, thus all isogenous curves do also. There are 4 curves in the isogeny class, hence no curve can have a point of order 8 defined over the rationals, and no curve can have a non-trivial point of odd order defined over the rationals either. Thus, E mod P, E mod Q, and E mod P plus Q are all cyclic of orders 2 or 4. So I will prove that this graph cannot exist. So first, let's assume that E is non-CM, and E mod P, E mod Q, and E mod P plus Q are all cyclic of order 4. then the image of the mod4 Galois representation of E is conjugate to H in the set of invertible matrices mod4. David Zywina proved that you need an element in the image of the Galois representation that behaves like complex conjugation, but H has no such element. If, on the other hand, E is Cm, then this is a question of finely many computations. There are only finely many J invariants that correspond to a curve E with Cm with a torsion subgroup Z2 cross Z2. No such curve or twist can give an isogeny-torsion graph of the form that we are trying to eliminate, so we are done. So here again is all the examples of T4 type graphs. So let's classify the S-type graphs next. These two S-type graphs were the hardest graphs to prove did not exist. Disproving the possibility of one of them is the same as disproving the possibility of the other because the difference is between a rational point of order 3. We suspected these graphs did not exist as we could not find examples in the LMSDB in a reasonable amount of time, but we were having trouble eliminating these graphs from the methods we developed before. A new hope came in the form of Harris Daniels, Alvaro's former graduate student who is now a professor at Amherst College. So let's start. An S-type graph is the fusion of these two types of graphs, a T4 graph like you see on the bottom left, and a 3 isogeny you see on the bottom right. So let E be a curve with an isogeny-torsion graph like the one we saw on the last slide, then E is necessarily non-CM. The image of the mod4 Galois representation of E is conjugate in GL2 mod4 to the group H, not just the subgroup of H, but the whole group H. So Jeremy Rouse and David Zurich-Brown classified all the two-adic images of Galois representations attached to non-CM rational elliptic curves. All curves with a two-adic Galois representation image mod4 conjugate to H are parameterized by the non-cuspidal rational points on the curve found in the RZB database with label X24E. We can find the J invariant of this curve X24E, which I wrote here in the variable T. If we add a 3 isogeny, all curves with a 3 isogeny are just non-cuspidal rational points on the modular curve X0 of 3. It does not matter whether you have a rational point of order 3 or not. The J invariant of these curves is written here with variable S. So equating and cross multiplying and doing some algebra, we get a curve C cut up by this equation with two variables T and S. This curve has genus 13, but at least with Falting's theorem, we know that there are finely many rational points. But what kind of rational points are these? Are these rational points cuspidal or non-cuspidal? What's going on? So we are lazy and hope they are non-cuspidal, so we won't have to put in any more effort in finding elusive rational isogeny-torsion graphs. Note that every power of t in the equation of the curve C is even. So there's an obvious map sending st on C to the point st squared on the curve C prime. C prime has the same equation as C, but the powers of t are just cut by a factor of 2. C prime has genus 6, which is a little better. Moreover, C prime has an automorphism psi given here. The quotient curve C prime has genus 2, and we can actually find a model for it. C prime is a hyperelliptic curve. Using a descent, we see that the Jacobian variety of C double prime has rank 0, so we can use Chabot's method to compute the rational points of C double prime. C double prime has two rational points, namely -2, -2, 1, and 1, 0, 0, which maps backwards to the points -1, 0, 1, 0, 0, 1, 0, 1, 0, and 1, 0, 0 on C prime. All these 4 points have t or s values equal to 0, and hence our cusps, the J invariants that I wrote here, would have a factor of 0 in their denominators, and that's bad. So like they said in the movie, Wreck-It Ralph, cusps are bad, and that's good. Cusps will never be good, and that's not bad. And so the two S-type graphs we are trying to eliminate, in fact, do not exist. So we are done. This is a question asked on Stack Exchange that inspired this question. And this is Alvaro's message that we are done. Okay, thank you.